Know what prime numbers are. They're numbers that are divisible by 1 in themselves. Let's talk about semi-prime numbers by way of example here, folks. This pi product notation does not mean 3.14. It means to take a product, not a sum. So let's take a look at a concrete example here. We'll use D. D is a standard, lowercase d is a standard letter for a divisor. We'll use the vertical bar divides. And then let's just do a semi-prime number, namely 10. Now 10 is not prime, but it's the product of two primes. That's what we mean by semi-prime. Any number that's the product of exactly two distinct primes is called semi-prime. Now we'll put a D right here. And this literally means to multiply all the divisors. Now 1's the gimme divisor, right? 1 is a divisor of 10, just like it's a divisor of any other integer. So we have 2 is a divisor of 10, and that's the only even prime number. 5 is a divisor of 10. And of course, the 10 itself is a divisor. Now this product here looks like it's going to be 100. 5 times 10 is 50 times 2 is 100. Okay? So again, we covered a couple things here. We covered the pi product notation, which we're going to use, and this idea of what is meant to be a semi-prime number. Now in general, if M is equal to PQ, the divisors are, if you just look at this as an example, the divisors would be 1, P, Q, and of course PQ, which is M, right? So you see there's semi-prime numbers have the property that they have exactly 4 divisors. Okay, so we're going to use that information right here to solve this problem. Okay, we have pi product notation of D divides M, where M is our unknown here. But we know that M is semi-prime. Now that gives us a remarkable amount of information. Remember how we had 4 divisors up here, 1, 2, 3, 4 divisors? So this notation, I'm gonna upgrade it just a little bit and use subscripts. D's kind of getting overloaded here, so we'll call the first divisor D sub 1, next one D sub 2, D sub 3, and D sub 4. There's 4 divisors of M. Okay, now again, we are trying to find M. Now as we saw earlier, you always have to have 1 as a divisor, so 2 definitely has to go right here. Okay, it'll be the first divisor that comes up for any integer is 1. If you increment it, you get 2. Now it'll take a little bit of time, but you can discover pretty quickly that 1408 is 2 to the 7th times 11. Now you'll see quickly that 1408 does not pass the divisibility test for 3 because 8 plus 4 plus 1 is not divisible by 3. Certainly not divisible by 5. There's a divisibility test for 7. Now the alternating divisibility test for 11 is useful here. Starting from the right, you can start either way, but you can write down 8 plus 0 minus 4. Is that what that is? Yeah, 8 minus 0. Let's put a minus there, plus 4 minus 1. Now that's equal to 11. So you're looking for a multiple of 11. 11 is a multiple of self. That proves that this is let me get rid of that right there. Okay, just mark it out so I don't have to go find the eraser. Okay. So that's why this is divisible by 11. Although by the time you went through all the 2's and just divided, it might be worth your time just to do that too. But anyway, this is the prime factorization. Now notice right here, if we are allowed 4 factors, right? So let's say we tried to put 2 to the 4th right here. Okay. Now you can think of this as 2 to the 1st, right? But you see, we can't put another 2 right here because we've already used up 2, right? So the only other possibility would be put the other 2 2's with 11, and that would be 2 squared times 11, right? But that's not even 4 factors, right? That's not even 4 factors, so this is no can do. So the only possibility here, and I'm going to write this directly beneath it, is to consider 2. Okay, and then we'll try 2 cubed. Okay, like that. Now, so we have 2, 2 cubed. So this would be 7 plus 1, right? And I'm doing it probably out of order for a lot of your taste. But another one, let's see, the 2 cubed minus 1 would be 7. So you could do 2 squared. And then finally, you could do 2 times 11. See there, folks? Now, without even knowing much here, look here, how many 2's do we have in this thing? We have 1, 4, 6, and 7, right? That's what we need. We need 7 2's, right? We have 1 here, 3, 6, 7 2's, and then the 11's left, right? But what does this give us, folks? What does this give us? Well, that would mean that D1 we're trying to find M, right? Okay. So we're all the divisors of M, D1 would be 1. Okay. D sub 2 would be 7 because we're subtracting 1 from 2 cubed. Okay. And the order is not particularly important here. D sub 3, okay. D sub 3 is going to be equal to 3, and that's good news because you see you're getting your semi-prime thing going on here. And then this is 22, so if you subtract 1, you get D sub 4 is equal to 21. Okay? And so you see, folks, these are exactly the divisors of 21, right? 1, 7, 3, and 21 are divisors of 21. And M is equal to the product, right? M is equal to the product. You see that according to this notation right here that we're using, M is equal to the product. So our M would be 21. And it's definitely semi-prime because you're accustomed to seeing it written like this. Okay? So M equals 21 is the answer to this problem, folks. Now, the semi-prime thing is important. Some kind of condition has to be placed on M or you're going to have a lot of different solutions. Like, try it out. I won't go through it, but let's just say we drop the condition that M is semi-prime, that it's any integer. Look at how many, you could get a lot of solutions to this. Based on this prime factorization, there's ways to go through here because you see the semi-prime thing is super powerful because it gives us 4 distinct factors. 1, 2, 3, 4, right? That's what the semi-prime does for us if you go all the way back to what we mean by semi-prime, right? But if you drop that condition, then you don't even know how many factors you have here. So it turns into a very difficult combinatorics exercise if you don't impose an initial condition on this constant M, okay? So let's go ahead and finish this thing off. We get M is equal to 21. I think that's the only solution. The semi-prime really imposes some structure, I think. I haven't really proved conclusively, I don't think. I wave my hands a little bit right here. You see, we gave it a whirl doing 2 to the first, 2 to the fourth, 2 squared. That's not even 3 factors, though. I don't even know how to get 4 other factors that are going to give you 408, keeping this prime factorization in mind. Okay? And notice that the only real computation we had to do, we weren't even thinking 1408. We were thinking about how to rearrange the factors in the prime factorization of 1408. Okay, so kind of a cool problem. I have not seen a problem like this. I think this may be a novelty. Let me know if I haven't seen this problem type in any of the number theory textbooks that I read. I'm not saying it's not there, but let me know if this is original. Very few things are original. There's not too much new under the sun these days in mathematics, but I've never seen this type of problem. Okay, thanks for viewing.